Welcome to the organic chemistry class. Today we are taking phenols and ethers. Yesterday we had something about the alcohols, that is hydroxy group attached to aliphatic system called alcohols we have completed. Today we will take whenever OH is attached to a simple benzene, such a compounds are called phenols. Even the simple, that is the pH stands for the phenyl with a ol, so therefore a pH OH symbol is given for the phenol representation. Ethers is simplest ether is a methyl plus O another methyl. This is called dimethyl ether. Dimethyl ether. And if a little bigger one, CH3, CH2, O, CH2, CH3. This is called diethyl ether. Diethyl ether. In fact, we have more, that is a typical example. In the case of phenols, we take ordinary phenol, and a typical example for the study of the ethers is a diethyl ether. This is also known as common ether or solvent ether. Both the sides we have ethyls, therefore it is diethyl ether, the nomenclature, and the rest we will take in the ether topic. Let us take first phenols. How these phenols are prepared? Preparation part we will take. We have four common methods are there. The methods which are common to the alcohols may not be suitable here. So, we have some special methods are there. The first method is somewhat common to the alkyl halides, but alcohols here the hydrolysis of first method is hydrolysis of chlorophenol. Hydrolysis of chlorophenol. Benzene, I am sorry. Chlorobenzene. Or phenyl chloride. Phenyl chloride or chlorobenzene. That is benzene, we are having here a chlorine here, that chlorine we are going to replace with a suitably with a OH group. You can guess what we have to take is a OH minus should be there to replace this Cl. But just taking the OH is not sufficient. We have to take the three different conditions. One is concentrated NaOH. Second one is a high temperature and high pressure. All these three conditions should be there. High temperature of approximately 350 degrees, that is not a big issue, but the high pressure is around 150 atmospheric pressure should be there. That is actually in the lab it is not possible. 150 atmospheric pressure in the laboratory we cannot maintain. Only industrially the method is possible. With all these concentrations, if you conditions, if you do it, a OH minus is replacing the Cl. It is a nucleophilic substitution reaction. Nucleophilic substitution reaction. It is commonly in the lab we cannot prepare. However, it specifications containing in the industry we can do. The process is also commonly known as Dow process. DOW, Dow process. It is a plural actually, Dow processes. Why plural? Means the temperature and the pressure you can alter. So, therefore, slight variations containing different methods are possible. All together we call Dow processes. But a specific method around 350 degrees and 150 atmospheric is a Dow process, single method. Okay. Now, let us go for the second method. It is a hydrolysis of diazonium salts. Diazonium salts. Benzene containing a N2Cl. This is called what? A benzene diazonium chloride. Here you need not to do anything, just add some water and warm it. Heat with water or boil it for some time. just boil it. The OH present here will replace the whole group. The N2Cl is a very labile or outgoing property containing group. Therefore, with a minimum of 1 OH, you need not to take base also, just water will replace and you will get the phenol. Only thing is, where from this N2Cl you are going to get? It is a small problem. In the benzene topic we have seen nitrobenzene reduction will give aniline. Aniline on diazotization with sodium nitrate and HCl at low temperature give this diazonium chloride. That on hydrolysis will give the phenol. Now, let us go for the other methods for the phenol. Third method, hydrolysis or fusion of sulfonic acid, benzene sulfonic acids are going to give this phenols. A benzene containing a sulfonic acid SO3H, this is called benzene sulfonic acid. This sulfonic acid also, because of the double bond outgoing property will be there. So, you can use the potassium hydroxide solid, and the sulfonic acid also happens to be a solid. You take solids, go on, heat it so that it melts, fusion reaction takes place. At that time, the whole group will be replaced by the OH minus. However, the OH with the phenol is an acidic compound. So, therefore, with the base it gives actually potassium salt of the phenol. O minus K plus, a potassium phenoxide is formed, potassium phenoxide, the salt of the phenol. This on reaction with the just water in presence of the acid, let us say H₃O plus, acidification or neutralization with this base with the acid, acidified water, then the neutralization takes place, you will get the phenol. This is also a simple method, not a complicated, but here the sulfonic acid is getting replaced by the OH, should get OH only, but because of the strong base it is in the form of salt is available. If somebody wants potassium phenoxide, it has a marketing facility, so directly you can sell it also, but if you neutralize it, you will get the phenol. Lastly, by oxidation of cumene. Cumene is a benzene containing a isopropyl group, 3 carbons in the middle carbon, if it is attached, it is called isopropyl benzene. The isopropyl benzene, a hydrogen in the center is a very reactive hydrogen, it is a tertiary and it is benzylic to this benzene, attached to benzene. So, therefore, it is easily oxidizable with the help of an aqueous NaOH medium. Send the oxygen or air, atmospheric air, pass the air through the alkaline solution of the cumene. Cumene is nothing but the isopropyl benzene. Then this hydrogen is replaced by the 2O with hydrogen. This peroxy group is introduced. So, this is the peroxide. Peroxide, one side cumene is there, one side hydrogen is there. Therefore, it is called cumene hydroperoxide. Cumene hydroperoxide. This peroxide is on reaction with the dilute sulfuric acid. The whole group undergoes a molecular rearrangement is taking place, and this 3 carbons with O becomes into a phenol, acetone, right? And the benzene with the OH becomes into the phenol. So, we get a phenol by this method. Acetone as well as phenol, both are very important for this particular purpose. So, therefore, in one method, in fact, this benzene and this cumene containing benzene can be prepared from the propene with the combination of benzene using a Friedel-Crafts acylation type. Therefore, that is propene is oxidized to the phenol, that is acetone, and the benzene is oxidized to the phenol in a common vessel, and that is the one of the speciality of this reaction. The rearrangement is also known as cumene hydroperoxide rearrangement. It is very popular reaction. However, we are not interested in the rearrangement, but we are getting a phenol from the some isopropyl group containing benzene known as cumene. Therefore, it is called from cumene by oxidation we are getting the phenols, right. Now, let us go for the properties of the phenol. Some properties of phenol. Phenol shows one important property known as acidic property, acidic nature. When compounds shows acidic nature, means especially with reference to the organic molecule, if a molecule loses one proton, you get an anion. That anion, if has got some stability, especially resonance stability or inductive effect stability, that it is ready to lose the proton. All the proton donors will become acids. Here in this case also, phenol is a molecule containing a benzene with OH. This OH, if it cuts and a proton is liberated, the rest of the molecule is now known as a phenoxide anion. Phenoxide anion. This phenoxide anion shows a beautiful resonance phenomena. Through that, the O minus first goes to the ortho minus, then this minus if it is given para minus, right, and the para minus if it is given, this goes to the again ortho minus, like that 1, 2, 3, 1 plus 3 resonance structures you are getting for this phenoxide. Totally 4 resonance structures are there, but one is originally phenoxide containing minus on the O, rest are the ortho minus, para minus, ortho minus, 3 resonance structures are cut. In fact, phenol also shows resonance. What is the greatness of the phenoxide resonance means, here when you write the resonance, O gets positive charge, in the ring you get a minus charge, whereas here a minus charge is delocalizing, therefore it is a charge delocalization. Resonance is a better one than the charge separation type of the resonance. Therefore, phenol always ready to lose the proton and become into the phenoxide, provided a proton acceptor is there. If this proton acceptor is not there, phenol cannot throw the proton and becomes into the phenoxide, isn't it? Some acceptor should be there, then the phenol donates this proton, readily becomes into phenoxide. Because of the resonance, it is getting stabilization. So, therefore, the reason for the acidity is the stabilization of the anion formed, that is phenoxide anion, right. So, the reason that is evidences is it reacts with sodium hydroxide. It reacts with the sodium hydroxide. It is a base, isn't it? So, with the base it is reacting and becoming into what? A phenoxide anion and the H₂O. That is sodium salt of the phenoxide is formed. Therefore, we confirm that the phenol is acidic. However, how much it is acidic means with sodium bicarbonate, for example, if you add, there is no reaction. So, therefore, it is base, but it is not strong. It is acid, but it is not strong acid. Phenol is therefore considered as a weak acid. Weak acid, not the strong acid. If it is a strong acid, it would have reacted with the weak base. So, weak base it is not reacting, therefore, confirms it is a acid, but it is not a strong acid, it is a weak acid. However, it also reacts with the sodium metal. And also you will get the sodium phenoxide plus hydrogen gas will be liberated. So, reaction with sodium metal as well as the sodium hydroxide confirms its acidic nature, right. Then we will go for the some of the properties of the phenol with reference to the ring. With reference to the ring, it is going to show some specific properties, that is especially electrophilic substitution reactions. Electrophilic substitution reaction is a characteristic reaction of the benzene. If you take alone, benzene also undergoes 5 reactions called the alkylation, Fiddlecraft alkylation, Fiddlecraft acylation, halogenation, nitration and sulfonation. All these 5 reactions you too can find here. Some slight variation or some difficulty, some favorability, all such points we are now going to receive. The one best reaction is halogenation. The best acceptable reaction is halogenation. In this halogenation, when phenol is taken, treated with the bromine, bromination. For halogenation, we are taking bromination. Just to take the bromine and dissolve in the water and then add. You find two types of the observation. One is phenol with a bromine at ortho plus phenol with the bromine at para. You get a mixture of the ortho para brominated phenols. When this is at room temperature, no heating, just bromine water, mix it and then add it, you will get the brominated. Instead of that, if you encourage this reaction also, you can find with water also, you can find a tribromo product. This product is called 2,4,6 tribromophenol, which is a white colored precipitate in fact. So, the reagent bromine water is going to give with phenol a 2,4,6 tribromophenol. The same reaction as I said previously, the bromine dissolved in CS2, which is a non-polar solvent, and the temperature is at 0 degree centigrade. That means much lower temperature if you take, then you will get only one bromo is getting into the ring, that is called orthobromophenol, and parabromophenol, a mixture is going to form. Parabromophenol and orthobromophenol products are coming. When the effect of the non-polar solvent decreasing the reactivity of the phenol, low temperature decreasing the reactivity, therefore the reaction. When you compare the benzene chlorination or benzene bromination, if you take benzene, how to prepare a bromobenzene? See the difficulty of this reaction, you have to take a concentrated bromine, first condition. You have to heat it for some time, and then you have to take a anhydrous ferric bromide as a catalyst. And how many bromines you are getting? Only one bromine. You compare this reaction with here. Here it is bromine is diluted, not concentrated, no heating, room temperature, no catalyst. Even then you are getting 3 bromines. How can you explain why too many bromines are coming without any effort? Means the credit goes to the OH group. OH has got the 2 lone pairs, one of the lone pair it donates and polarizes the pi bond to ortho, para and ortho subsequently. Therefore, if a bromine is taken, you get a bromonium ion is attacking species that can be readily attacked at ortho, para, ortho. That's why ortho, para bromination is taken. However, you can balance it. 3 bromines are entering and 3 H's are replaced by the bromine. Therefore, 3 HB are coming. Totally 6 bromines means 3 bromines are utilized. That's a different issue. But the question is, compare the bromination of the benzene, bromination of phenol. Phenol undergoes a very easy or facile bromination because of this OH effect, this electron donation showing the resonance. You can call it as a plus M effect, plus mesomeric effect. So, due to the plus M effect, the OH is 2 qualities it is showing, ortho-para directing property as well as it is a ring activating. That's why the reaction has become a much more easy, or the 3-fold reaction is taking place. Okay. If you control with low temperature and non-polar solvent, only 1 bromine is coming. Okay. For halogenation, it is the wonderful observation in the case of phenol that the phenol is very reactive. Okay. Right. Now, the second is the nitration sulfonation. You can take the nitration reaction. Phenol undergoes again a very easy nitration. Compare the nitration of benzene. Benzene needs a concentrated H1O3, concentrated H₂SO4 and heat it around 70 degrees centigrade. If you heat it, you will get a 1 nitro group. With all this difficulty, what is the difficulty? Reagent is concentrated, a catalyst is used, sulfuric acid, you are heating. Now, see the phenol, how best it is going to react. The phenol, you just take dilute sulfuric acid, dilute HNO3, that's all. Then at room temperature, no heating at all, you will get a orthonitrophenol plus paranitrophenol. Paranitrophenol mixture is going to form, however. Okay. Now if one of this the condition is imposed, what is that? Either you take concentrated nitric acid or catalyst taking or heating, if you get a trinitrophenol is formed. Trinitrophenol is a explosive chemical also, which is also known as a picric acid. Picric acid. Because this some problem in the nitro group arrangement, it undergoes a explosive. It's a explosive. Just like several chemicals like trinitrotoluene and so on explosive, this is also an explosive picric acid. It is actually no COOH function. Sometimes the question may be asked, what is the functional group present in the picric acid? We think that there is a COOH group because COOH shows acidic. But there is no acidic group, isn't it? The OH shows acidic property because of the 3 -I -M groups. The OH acidity is almost equals to the on par with the carboxylic acid. Therefore, it has become a stronger acid. It is a strong acid and it is able to react with the sodium bicarbonate also. Just now we said phenol will not react, but this reacts. This compound is going to react, unlike the phenol, it is going to react. That shows it is a strong acid, right? Now, similarly, sulfonation. Sulfonation also with the sulfuric acid takes place at ortho and para. Phenol observes two types of the sulfonations. At dilute sulfuric acid is enough to promote the reaction. And you have one observation, around 20 degrees centigrade, you will get a orthosulfonic acid. Orthosulfonic acid. At 80 degrees or so, same temperature, parasulfonation is taking place. This is one speciality here. Sulfonation takes place at ortho at low temperature, at high temperature, parasulfonation is taking place. However, we have one problem with this, the last two. D and E happens to be the Friedel-Crafts alkylation as well as acylation. Both the reactions have some problem. Phenol has got some problem in this reactions. It's a failure reaction on the phenol. What is the reason means? Friedel-Crafts alkylation is taking place with the help of the RX in presence of the anhydrous aluminum chloride. What is the role of the aluminum chloride, if you can understand? The aluminum chloride holds the X minus temporarily, that is the role. If water is there in this mixture, that is called what? Hydrated aluminum chloride. The water lone pair will fill this aluminum chloride gaps. This is the vacant orbital. The Rx cannot be, X minus cannot be held by the aluminum. That is what happening. That is, if aqueous aluminum chloride is taken, reaction fails. Similar to that, when phenol also a lone pair enters into the vacant orbital, so the aluminum chloride vacant orbital is filled. Therefore, the Rx cannot be break. Moreover, if R plus is generated by taking the more quantity aluminum chloride, R is undergoing a reaction with the phenyl group rather than the OH. That's why the Friedel-Crafts alkylation acylation is a failure reaction. However, for the acylation, we have one indirect method is there. Take the phenol salt, sodium salt, and acid chloride you take. Acetic acid, for example, acetylation, phenol acetylation, have you do, I am explaining. Sodium salt of the phenol plus acetic acid chloride, if you take, the NaCl will eliminate and the phenol will become into an ester. OCOCH. This is known as what? Phenyl acetic acid. So, therefore, phenyl acetate. Phenyl acetate. The straightforward reaction of phenol and acetic acid is not that favor. Therefore, sodium salt and the chloride, that is acid chloride of the acetic acid, and the sodium salt of the phenol is taken. This is called Schotten-Baumann reaction. SCHOTEN, Schotten-Baumann reaction. The name reaction Schouten-Baumann. It is nothing but an improved esterification. In the esterification, alcohol and acid will be taken. Here, acid chloride is an activated form of the acid. The sodium salt is taken, just like Williamson synthesis. NaCl is removed and an ester is formed. This ester, when you heat it with anhydrous aluminum chloride. Now see the role of aluminum chloride. The lone pair and the O will be attacking here. This whole group will be detached as a CO and the CH3. This works as an electrophile and goes to the ortho and the para. So therefore what you will get is a phenol with a ortho-acetylated. That means direct phenol you cannot introduce acetylation. Introduce acid group onto the O and then heat it with aluminum chloride. The acid group is migrated to the ortho as well as para also. You also get a para-acetylated phenol also. Both this migration of acid group from O to the ring is a molecular rearrangement. This type of reactions are called rearrangement reactions. It is specially known as a freeze migration or FRIES, freeze rearrangement. The name reaction once again. What is freeze rearrangement? A phenyl acetate, when you heat it with aluminum chloride attacks on the O, releases this COCH3, that acts as an electrophile, attacks at ortho and para, replaces the hydrogens. This hydrogen goes back to here. So therefore an exchange of hydrogen versus the acid group, that is a rearrangement reaction known as freeze arranged. This allowed this reaction that is identified. Therefore it is known as freeze rearrangement reaction. Phenol undergoes some colors giving reactions. Phenol undergoes a reaction with ferric chloride, with neutral ferric chloride. When you add phenol, you will get a violet coloration. The coloration is due to the phenol makes a complex with this iron ion. Fe+3 is a 6 types, that is 4 sides 4 and 1 on from the top, 1 from the bottom, 6 phenols on each corner, 1 phenol will be there. Okay, like this 6 phenols will be on the 6 sides as a neutral molecules, acts as a ligands. So you can write the complex like this: iron with the phenol 6 times. A complex ion is formed, a complexation taking place. That's why this reaction is a violet coloration reaction is giving. Phenol also gives with the phthalic anhydride. If you take phthalic anhydride, phenolphthalein is formed. This phenolphthalein, when you add some sodium, this is now in the acidic medium. In the sulfuric acid, if you add and heat it, you will get phenolphthalein. This phenolphthalein in some sodium hydroxide, if you add alkaline medium, you will get a pink coloration. This is also one of the tests for the phenol. How do you identify phenol? Means phenol with neutral ferric chloride, violet coloration, phenol with phthalic anhydride, followed by acidic, that is alkaline medium, you will get a pink coloration. These are the beautiful tests for the phenol. Now let us go for some properties of the ethers. As I said, ether contains a formula called ROR. These examples will be CH3OCH3. And similarly CH3, CH2, O, CH2, CH3. Here we have a small point on the nomenclature also. One of the branch is taken as alkane. This is taken as a alkane. And this group is called as a alkoxy. Alk goes on changes, depending upon the number of carbons. In this case, 1 carbon alk, therefore it is called methane. This 1 carbon alcohol, that is called methoxy. So what is the IUPAC name of this compound? Alkoxy containing alkane. So now apply that nomenclature to this one. This is ethane. So this is called ethoxy. Therefore it is called ethoxyethane. Common name is dimethyl ether, diethyl ether, and so on. If the alkane is propane, the methoxy can be on the first carbon, methoxy can be on the second carbon also. Here also methoxy group can be there. So, the first one is called 1-methoxy propane. Second one is known as 2-methoxy. The methoxy is on the second carbon. So, therefore, 2-methoxy propane. Okay. So, like that you can have this one. The ethers have one speciality. For example, if you have a C2H6O, with this formula you can write a compound ethanol also, CH3CH2OH, as well as a CH3OCH3. These two compounds are differing in the functional group itself, therefore, they are called functional isomers. These two are called functional isomers. Whereas, here if you see the 1-methoxy propane, 2-methoxy propane, ether function is same, only position is differing, therefore, they are called positional isomers. Not chain, looks like chain, but it is positional isomers, right? Now, the alcohol and methyl ether, they are functional isomers. One of the specialities, this hydrogen linked to the another ether O, that is alcohol O. This has got a delta minus, this has a delta plus. This type of bonding, that is C2H5, let us say, bonding between a delta negative charge of the one alcohol, delta positive of the another alcohol is known as what? Hydrogen bonding. Because of this hydrogen bonding, the alcohols will have a higher boiling point. In the case of ethanol, around 79 degrees centigrade you find. Whereas the same structural formula is 2 carbons, 6 hydrogens, everything is same, but it will have around minus 25 degrees centigrade boiling point. See how much difference, almost 100 degrees difference is there. This is a very, very low boiling point. Why means this only will have a small delta negative, but there is no delta positive nature on the molecule. Okay, just polarization delta negative, delta plus on the carbon will be there, but this delta plus and delta minus will be very small, because the CO bond is not much polarized. This, whereas OH bond is a much polarized. The accumulated positive charge and a small sized atom can contribute to a stronger bond known as hydrogen bonding. This develops only dipole attraction, but not the hydrogen bonding. So, the reason for the why ethers will have a lower boiling points means there is no hydrogen bonding, that is why they will have a very low boiling point. Corresponding molecule will have a hydrogen bonding, therefore, higher boiling points. That is the one point to note in similarly, the alcohols are highly soluble in the water, whereas ethers are insoluble in the water because of the absence of the hydrogen bonding. Now, let us see some preparations of these ethers. One of the method is alcohol is heated. Ethyl alcohol you take and heat it in presence of concentrated sulfuric acid at around 140 degrees centigrade. As we have seen in the last class, at 70 degrees it gives a ethyl hydrogen sulfate, at 140 ether comes, at 170 you get a alkene formation. Dehydration takes place within the molecule alkene. This should be 140 degrees, or Al2O3, alumina at 250 degrees centigrade also will give the ether. If it is 350, you will get alkene formation. Okay. So, therefore, the reaction leads to give the ether formation with an expulsion of this water molecule is removed. It is a dehydration between the two molecules, intermolecular, the dehydration taking place, ether is formed. From one side OH, one side hydrogen is removed. The same reaction is improved by a scientist called the Williamson synthesis. He won a Nobel Prize for this reaction, Williamson synthesis. The greatness of this reaction is, in the first case we have some problems. One is the low percentage. One first problem is a low percentage, the product is formed very less. Second one, it has got the side products, lot of side products are there. If slight temperature, if it increases, it goes to the alkene formation. Less temperature, it goes to the formation of the ethyl hydrogen sulfate. The third problem is mixed ethers, it is not suitable. Mixed ethers. Mixed ethers means what? For example, if you take a methanol and ethanol, we are supposed to get what? Methyl and ethyl ether, isn't it? So, methyl and ethyl will join, but you also get the dimethyl ether and diethyl ether also. because we cannot take one molecule and join it. We have to take huge number of n molecules of methanol, n molecules of ethanol. If you take some methyl also, just like Wood's reaction, ethyl also react, therefore all three will come. This becomes a homologous series. Homologous series will have a small difference, only CH2 unit difference. Therefore boiling points are very close, the separation needs a very tough job. So therefore nobody will prepare a methyl ethyl or a mixed type of ether by mixing the two different types of this one. Instead we have a method here. Williamson proposed one alcohol you take in the form of the, for example, ethyl alcohol, you take in the form of the ethyl chloride. You just treat it. Ethyl alcohol you take, how you prepare alkyl halide? You can add PCl5 or PCl3 or thionyl chloride or Lucas reagent and so on. Any one of the reagent will convert ethyl chloride into the ethyl alcohol to ethyl chloride. Now what you add is, now one ethanol you take and convert into the sodium salt. By adding the sodium metal, you will get sodium ethoxide. Okay, right. Now what happens is, if you add these two, no catalyst, nothing, no catalyst, no heating and no other conditions, just ethoxy group will replace the Cl. This happens to the one of the wonderful nucleophilic substitution reaction, because ethoxide is a very strong base which will attack on that and replace the Cl. You will get the ethyl and ethyl ether. Okay. So the pure quantity of the ethyl ether coming and high percentage is formed, no much problem here, no heating, no catalyst, nothing. Similar the case, if you take methyl chloride and sodium ethoxide also, you won't get any byproduct, just sodium ethoxide, NaOA. So O minus will attack and you will get the methyl and the ethyl ether. So the Williamson method is happens to be the one of the best method for the preparation of the alcohols, ethers. You can also use a silver oxide or some methods, but the two methods are enough. Let us go for some properties of this ethers. Alcohols, ethers are very stable. They are very stable, used as that's why several times as a good solvent. What is solvent? Solvent is a one which won't react with the chemicals, but it will dissolve the both the side substances so that it works as brings into a common field. So ethers are working as a very good solvent because of the very stability. Why the stable means there is no reactive hydrogen present in the ether. However, ethers are going to react with the one important reagent is a HI. With the HI, there are two types of reactions. The one is a dilute HI or the cold HI, or you can say 1:1 ratio HI. When you add only one side breaks, one will become alcohol, the other one will become alkyl iodide. That is the reaction. The other way is the concentrated HI or the hot HI, or you can say excess of HI. Excess of HI, if you add, both the side reaction takes place, both the sides you will get alkyl iodide and alkyl iodide. What happens to the oxygen? Oxygen becomes into H₂O. So 2 moles of alkyl iodides and 1 mole of water is formed when excess of HI is taken. When 1:1 ratio, that means 1 ether, 1 HI. Measuring equimolar quantities if you take, you will get the alcohol and the alkyl iodide. This question also several times asked in the IIT examinations. Ether with the 1 HI if I add, you will get the alcohol, ethanol and the ethyl iodide is formed. Right? If 2 moles of HI is added are excess condition, these are all excess condition, this is a insufficient condition. Excess condition, if you impose both the sides you break, you will get the 2 moles of ethyl iodide and the water. Right? So the question, so many times this question is being asked, whether the 1 mole what happens, with the 2 moles what happens. Ethers have got the another reaction is ether bond is you can cut with dilute sulfuric acid or H₃O plus. you can hydrolysis, you can observe, one will become alcohol, that means we are adding HOH. So, both the sides you are getting ROH, so 2 moles of alcohol will be formed. Okay. Ether has no other reaction excepting this HI and the hydrolysis reaction. However, and the long standing, okay, peroxide formation. Ethers on a long standing, that is in a half filled ether bottle, if you keep it for a longer time, slowly ether goes to react with the air present in the bottle, that is oxygen. One of the alpha hydrogen that is present on the first carbon is going to react with this O2, and what you will get is you will get a OOH bond. This is called peroxy bond. This OO bond is called peroxy bond. Therefore, it is called peroxy ether. Peroxy ether has one the dangerous property. What is that? Explosive property. So, therefore, if you have a old ether or stored ether, if you heat it, instead of evaporating, the compound undergoes explosive. Then what to do with that ether? You need not to throw it away, this ether. This ether may be treated with a freshly prepared ferrous sulphate. It will have a F2. +1, +2, isn't it? Fe +2 situation, ferrous sulphate, light green color will be there. A freshly prepared solution you have to take, and that is dissolve in water and take it, mix with this explosive, that is peroxy ether, and shake well. This O2, one O will be liberated and converting this ferrous sulphate into the ferric sulphate +3. SO4 will be like that. You have to take it as a 3 and 2. So, ferric sulphate, which is a brown color solution. So, the light green, when it turns to the brown, it is an indication that the ether has peroxy ether. So, what to do is, you go on shake like small quantity of this light green color, you add solution, shake it, it will become brown. 2-3 times if you shake it well with this green color, finally this ether will be purified, you will get the pure ether. So, after that if you distill it, you will get the pure ether. This is a purification of ether also. What is the contamination here? That is peroxy ether, which has got an explosive property. Therefore, ethers are taken care while handling the old ethers when you take this. So, let us go for the some of the questions. If necessary, we will have a discussion later part. This first question. Identify the product in the following reaction. This is a phenol question. Phenols undergoes last in the chloroform topic we have seen, when phenol is treated with the chloroform NaOH. A name reaction in the chloroform topic we have covered, that is why I just skipped it. Chloroform NaOH. The chloroform reacts with NaOH, first gives the CCl3 minus, from which it is a CCl2 is liberated, which is called what? The dichlorocarbon. This dichlorocarbon acts as an electrophile, attacks at ortho and para. Therefore, ortho CCl2 attacked compound comes, however, it undergoes hydrolysis. Finally, it gives an aldehyde function. So, therefore, ortho-formylated phenol, which has a common name salicyl aldehyde. The name reaction, it is known as Reamer-Tiemann reaction. Plus, it's para isomer also, because CCl2 can attack and also at para, therefore, para isomer also coming in the answer. Therefore, second answer, that is salicyl aldehyde, is the right answer. But you also get para isomer also, one of the product. The order of reactivity of phenol, nitrobenzene and benzene. As I said, phenol has a OH plus M group, it is activated. Nitrobenzene, nitro is a minus M group deactivated, benzene is in between. So, therefore, what is the order? Phenol, nitrobenzene, after that it is benzene. So, therefore, 2, 1, 3 and 2, 1, 3, 2, that is the answer. 3 is the right one. Next. The conversion of orthoacetylated, just now we have seen orthoacetylated phenol in presence of aluminum chloride, carbon acetylated, that is ortho or para, you will get it. C-acetylated phenol is an example for the type of the reaction. Molecular rearrangement, it is known as Fries migration or Fries rearrangement. So, answer 3 is the right answer. Next. Phenols have this particular reaction also. Several times this reaction is repeated. It is not that important, but as far as this EAMCET is concerned, any ether, if I take for example a diethyl ether, when it is treated with the carbon monoxide in presence of the anhydrous, the BF3, heated at 150 degrees centigrade and 500 atmospheric pressure. 500 atmospheric pressure means very highly the pressure condition. So, we have a normal pressure at 1 atmospheric pressure. This heat is not that difficult, 150 you can maintain, but 500 atmospheric pressure is highly. This one, the CO group comes in this place, that is and you are getting insertion here a 2 carbon, but the 3rd carbon will become this C double bond O and this O, that is totally the CO is being inserted here. It undergoes a reaction, gives the a propanoic acid with ethyl. This is known as, first you have to say ethyl in the nomenclature of ester, ethyl propanoate or propianoate. Ethyl propanoate, an ester is formed, carbon monoxide and boron trifluoride is the reagent. Next. So, which one of the following gives yellow precipitate with iodine and NaOH? This is in the chloroform topic we have seen. However, this acetaldehyde is going to react this and gives the iodoform formation takes place. Answer is 1. Next. What are X and Y in the following reaction sequence? Ethanol on chlorination, you will get a oxidation reaction, that is acetaldehyde comes. Acetaldehyde when chlorine treated, trichloroacetaldehyde is formed, that is chloral is formed. So, answer goes to the acetaldehyde, trichloroacetaldehyde, that is answer 3. Next. The correct order of reactivity of the hydrogen halides with ethyl alcohol. Ethyl alcohol when treated with HX, you will get ethyl halides. For that reactivity order is the Hi is the best reagent, followed by the HBr, followed by HCl and the HF. So, ready to break is Hi in the case. So, therefore, answer 4 is the right answer. The IUPAC name of this particular ether, one side ethyl group is there, the other side isopropyl is there. You can call commonly ethyl isopropyl ether, but the isopropyl is taken as a propane and the ethoxy is said as a 2-ethoxypropane. 2-ethoxypropane is the IUPAC name. Answer 4 is the right answer. Next. The functional group present in salol. So, the phenol when treated with the carbon dioxide, in presence of the base like sodium hydroxide, you dissolve the phenol in the sodium hydroxide and then heat it with the carbon dioxide with the pressure also. The carbon dioxide is acting as a electrophile with having vacant orbital. It attacks at ortho as well as at para also. Therefore, 2 types of the answers are coming. So, the phenol with the carboxylation, this reaction is known as carboxylation, plus its para isomer also coming, that is COOH at para. The reaction is known as a Kolbe-Schmidt reaction, SCHMIDT. This is a Kolbe-Schmidt reaction. Kolbe-Schmidt reaction. We have Kolbe electrolysis also in the alkane chapter. This is a Kolbe-Schmidt reaction. In this reaction, CO2 is introduced, therefore, it is called carboxylation. What is happening in the Remer-Timer reaction in a formaldehyde group, therefore, it is called a formylation. Phenol formylation is known as a Remer-Timer reaction, phenol carboxylation. Now, this compound is known as what? Commercially very useful, known as salicylic acid. Salicylic acid. The salicylic acid has one or two derivatives, like for example, if this is treated with the acetic anhydride, or acetyl chloride, the H is replaced, you will get the acetylated salicylic acid, acetyl group containing salicylic acid. This is known as aspirin. Aspirin is a very good analgesic drug. It as a painkiller we are using. Similar the way when it is treated with the methanol, that is this COOH becomes into ester called COOCH3. So this is called methyl salicylate. Is known as oil of wintergreen. Similarly, when it is treated with the phenol, so this methanol will become a phenol now. That is called salol, COO phenyl. This OH is free, this is known as salol. So salol is a phenyl salicylate. What is the functional group present in the salol? A OH and a ester function. Therefore, the last answer, fourth answer is the right answer. Salol is also a very good analgesic drug. All are derived from the salicylic acid, which is derived from the phenol by carboxylation reaction. Hybridization of oxygen in diethyl ether. Diethyl ether contains 5 atoms, 4 are carbons, all are containing sp3 hybrid, including the oxygen also. The question is not specified whether it is oxygen or carbon, but all the atoms will have sp3 only. So, therefore, answer 3 is the right answer. Next. Which of the following compounds when heated with the carbon monoxide 150, that is ester is formed ethyl propanoate? Answer is 3. Just now we have seen the insertion of CO group, it becomes into an ester, that is ethyl propanoate. Ethyl chloride reacts with the sodium ethoxide to form a compound A, and that is ethyl chloride with sodium ethoxide means it is a Williamson synthesis. Ether is formed, the yield A is a ether. The answer is 2 here. Ethanol and sulfuric acid is the requirement. In which of the following reaction the product is an ether? Again here Williamson synthesis must be the reaction. So, in the ether if you want, you take the ethyl chloride and sodium ethoxide. Answer 4 is the right answer. Next. Identify A and B in the following reaction. So, ethyl chloride with something you got the ethanol, ethyl chloride with something again you got the ethanol. So, what must these two means? One must be the aqueous KOH, the other one is also similar to that aqueous KOH must be the silver hydroxide or moist silver oxide, maybe also the answer 1 is the right one therefore. Next. A diethyl ether with carbon monoxide with BF3 150 500 atmospheric pressure, an ester is formed which is a ethyl propanoate, that is answer 4 is the right answer. Next is answer is 4. So, answer 4 is the right answer. 16th one. Which one of the following gases is liberated when ethyl alcohol is heated with ethyl magnesium iodide? See here the reaction is like this. RX when treated with the magnesium you will get the RMGX. The RMGX when added water, the R will take H, RH will come. So, in the alkyl halide whatever the number of carbons you take, same alkane is liberated. If ethyl chloride is taken with magnesium, you will get a ethyl magnesium chloride. Hydrolysis with water, you will get the ethane, right? So, if you take propyl chloride, you will get propyl magnesium chloride, propane comes. So, you have taken a ethyl alcohol heated with the ethyl magnesium alcohol. Instead of water, you can take any alcohol. which gives the H. The H goes to here, becomes into alkane. So therefore this R is immaterial, whether you take methanol, ethanol, phenol, any proton donating is no matter. So therefore whatever the RMGX is going to give the alkane. So ethyl magnesium chloride will give the ethane. That is answer 2. So which one of the following compound gives aspirin as the reacting with acetic anhydride, that is salicylic acid, that is second one. The salicylic acid we have seen just now, salicylic acid with the aspirin is formed, that is acetylated salicylic acid is known as aspirin. Answer 2 is the right answer. Next, the products formed when diethyl ether is reacted with cold HI. Cold HI, as I said, it is a insufficient HI, or 1:1 condition is equivalent. So therefore one becomes alcohol, one side you will get ethyl iodide. So first answer, ethyl iodide and ethanol is the right answer. Next, chloroethane reacts with X to form diethyl ether. So ethyl halide is becoming ether, means you need a ethoxy group. So ethoxy group, when you add ether comes, what is X means? Sodium ethoxide is the answer. So answer goes to the third answer, sodium ethoxide. Next, Ethyne is treated with 30% sulfuric acid in presence of 1% mercuric sulphate. The ethanol, that is ethanol aldehyde is formed. What is the product formed? Ethanol, that is a alkyne chapter or acetaldehyde chapter it goes actually. Okay, doesn't matter. The answer 3 is the right answer. Which one of the following reaction does not yield an alkyl halide? Does not yield an alkyl halide. Ether bond when treated with HI or PCl5 thionyl chloride, somehow you can prepare the alkyl halides, but not with the chlorine. With the chlorine there is no reaction, ether will not react. So therefore answer 1 does not yield alkyl. Answer 2 is wrongly given. Answer 1 is the right answer. An isomer of ethanol, dimethyl ether is the right answer, because the ethanol contains 2 carbons, dimethyl ether also contains 2 carbons. Formula will be same. Next, when an alkyl halide reacts with an alkoxide, the product is one RX, other one is alkoxide. So there is a nucleophilic substitution leading to give the ether formation. As I said, this is a Nobel Prize winning reaction. We have a lot of philosophy in this reaction. In fact, that is the byproduct. Sodium chloride will be the byproduct. If 2 alcohols, if you take, water is formed byproduct. If alkoxide and alkyl halide is taken, sodium halide is formed. Sodium halide happens to be more stable than water. As the byproduct increases, our product also increases. Side product increasing is dangerous for us, but the byproduct increasing always encourages the main reaction also. So that philosophy makes the reaction here. It is the ether is the answer. Next, diethyl ether is prepared by passing ethyl alcohol vapors over a catalyst under high pressure and temperature. As I said, diethyl ether can be prepared from the alcohol. Alcohol has 3 conditions. At low condition, ethyl hydrogen sulphate. At normal condition, ether is formed. At higher conditions, undergoes a dehydration, gives alkenes. Here through alumina it is possible here. The temperature is not mentioned, but around 140 degrees. If alumina use 250 degrees centigrade is required. Next, old bottles of ether are dangerous because they frequently contains high concentration of peroxides. As I said, peroxy bond is a very unstable bond, and this peroxides carrying or a small impact on the peroxide will explode. So therefore old bottles of ether is not advisable to handle roughly, or the ethers, if you heat it for the distillation purpose for preparing pure ether, is also not advisable. At a lower concentration doesn't matter, ether distill out, but as the ordinary ether comes out, peroxy ether will be restored in the flask. After certain concentration, the peroxides undergo explosion. So therefore old ethers are bottles containing for the longer time kept aside, should not be handled without nullifying these peroxides. How the peroxides are removed? By adding the the ferrous sulphate, shaking with the freshly prepared ferrous sulphate will have a green color. If peroxides are there, the ferrous sulphate green color changes to the red, becoming a ferrous sulphate into ferric sulphate. That is also test for the peroxide ether, whether it is there or not. This confirms the most of the questions of the that is ethers and the phenols. In the next class, we will go to the next topic called carbonyl compounds, which contains aldehydes and the ketones. Thank you.